In this video, we're going to talk about problem solving, and we're going to actually discuss strategies and techniques and look at some problems and try to solve them. And let's start with a problem to try to solve. Let's say I wanted to find the sum of all the numbers from 1 to 100. So I wrote that out as 1 plus 2 plus 3, dot, 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 all the way down to 100. In fact, this is actually a famous problem. This problem actually, here it's famous. And it came from a mathematician whose name was Gauss when he was a kid. And he was so smart. He kind of started to annoy his teacher, right? Because he would like finish everything so fast compared to the other kids. So the teacher was just kind of fed up with him and was like, I need to give you some busy work so that you leave me alone for a while. Here, go add the numbers from 1 to 100. Thinking, Gauss is going to do 1 plus 2, which is 3, and then do 3 plus 3, which is 6, and be like, cool, yeah, go on. But Gauss then went and found a pattern, came back to the teacher very quickly and was like, okay, I did it. And the teacher was like, what the hell? How did you do that? All right. So let's see how Gauss figured out a pattern for solving 1 to 100. So what he started with was noticing, okay, so let's start with the first three numbers. And I'm also going to do the last three numbers. I don't really want to list out all of these. And the last three would be 98, 99, and then 100. Okay, so what Gauss noticed was that when he looked at the first number and the last number, he was like, 1 plus 100 is 101. Okay, that's easy. Cool. And then Gauss was like, okay, 2 plus 99. Oh, hey, that's also 101. And he was like, 3 plus 98. That's 101. And he realized he could keep doing this through all the numbers. If he kept adding them up like this, they would always add up to 101. So how many pairs of 101 do we have? Well, the answer is 50, right? Because basically cutting 100 in half. So grab your calculator. If you don't have your calculator, go get it. All right. Take a moment, pause the video, get your calculators. We're going to use it. And then take 101 times 50 in your calculator. And I plugged mine in and I got 5,050. You're amazing, just like Gauss. Okay, good job. All right, so let's look at another problem. And then we're going to kind of start talking about strategies. All right. So this one we kind of looked for like some interesting patterns. All right, so this one's kind of an interesting problem. The scenario is, and pause the video, draw this out so you can do this. I'm sorry that I have the first couple problems already written out because I ended up having to re-record because there was an issue. All right, so we're gonna draw a line between the common letters, and you can't cross other lines and you can't go outside of this rectangle. Okay, so just to kind of show you what I mean, the idea is, let's say I connected, oh, I just realized I had the wrong letters here. Swap those, just kidding. That would be very easy. This is supposed to be C and that's supposed to be A. There we go. All right. Let's say I connected A to A, but when I go to try to connect B to B, boop, can't do that, right? Can't cross it like that. What I could do though, I could be clever and I'm like, hey, I could do that. But now I have a problem with C, right? C doesn't really want to connect. So I'm like, crap. Okay, so I want you to take a second, think about this. Try to see if you can come up with a solution. Pause the video, give it some thought, all right? And then once you've given it a little bit of thought, like give it a couple drawings, all right? See if you can come up with something. I'll give you a hint, all right, on how you could do this. Okay, so let's go ahead and look at a hint. So here, let me scooch up here. I'm going to redraw this, but this time I'm going to change where A and C are. So I notice that the letters at the top all touch the side, but only one letter at the bottom touches the side, B, right? So A and C are kind of floating, and that matters. So what if I were to bring A and C to the middle, like right here? Okay. If I did that, and I wanted to connect A to A, no problem. C to C, no problem. But to connect B, I would actually have to go around A and C. But there we go. I did it. So B connects. I'm going to use that reasoning up in the original picture. Okay. I'm noticing that I needed to go around two of them in order to connect B to the other one. All right. So let's use that logic here to try. So let's go ahead. I'm going to connect A to A, just like I started there. Okay. And then I'm going to connect C to C. All right. So to do that in this picture, I'm actually going to have to take C and go around A and then touch C. Boop. Cool. Okay. But now to connect B, I need to go around both A and C. And look, that'll work, right? Because here, I'll do it in a different color. So B, if I go around A, and I'm going to squeeze in here, and come over here, and C, boop, there we go. And if you figured that out, that's awesome. I'm super impressed with you. Because I didn't figure it out right off the bat. I needed some help. All right, so there you go. That's kind of how you can rethink the problem. So it's noticing that in this problem, understanding what was kind of happening here, that A and C were floating. So I kind of was like, well, what if I put them in a different location and kind of make it easier on myself to see what happens? And that's how you can come up with the solution. Okay, what we're heading towards here, though, is a way of thinking of problems. And this is a mathematician, Polya. Polya came up with this problem solving strategy here. Let me switch back to black pen here. Okay, Polya's problem solving strategy says first thing you want to do is understand the problem. And this works for all of them. You got to understand what you're being asked. In fact, sometimes that's the hard part, right? What are they asking me to do here? Making sense of it, making sure it is clear. Then you want to devise a plan. Next hard step, okay? Because the idea is we have to come up with something. We got to try something, think of something, and give it a shot. And that's the next step, giving it a shot. So carry out the plan. So you come up with a plan, try it, and then you need to look back and see what happened. Did you solve it? Did you make a mistake? Is there an easier way to solve it if you did solve it? Like, is there a different way you can approach it? Because sometimes you can approach problems multiple ways. That's the idea behind Polya's strategy here. In fact, the first kind of strategy we're going to use, we're going to talk about a few techniques, okay? And the first one is make a model. And I'm going to revisit the problem we talked about earlier, but I'm going to do a simplified version of it. So instead of summing 1 to 100, I'm going to sum 1 to 6. And instead, I'm going to use a different strategy here. Hold on, let me scroll down. I don't want to see the next problem yet. It's just more writing on my paper than I want to see. Okay, cool. So instead of finding that pattern, which I could use right now, I could totally use Gauss's technique, but I want to try something different. I'm going to model these numbers here. So a model of the number 1 would be, let's just draw a single block. And then the number 2 would be 2 blocks. But here, I'm going to put it right next to it so that I see them individually. So there's the number 1 and the number 2. Okay, number 3 would be 3 blocks, 4, and then 5 and 6. So I've made little block towers, starting with 1 block, going up to 6 blocks. There we go. Okay. Little block tower with 6 blocks, pretending that that's not messy. Okay. Here's what I'm going to do. I want to find this sum, and I could literally count them out, but the idea is I'm going to look at really large numbers, right? So I want to be clever. I want to come up with a way of without listing them all out like this, that I could solve with really large numbers. Okay, so here's the idea. They were tricky. They said, okay, what if, since I'm using a model here, what if here, let me switch back to the green pen, were to take this like same shape and like mirror image it, right? Like kind of across the diagonal here. So in other words, here, I'll start with a 1 here and then 2 blocks here, 3. Here, let's just do it like this. There we go. 1, 2, 3, 4, 5, and 6. Okay. So the idea is I've created kind of a mirror image of this so that it formed a rectangle, which is a much easier shape for me to work with because I can see that on this side of the rectangle, I have 7 blocks, and this side has 6. The original 6 I started with, 6 columns of blocks, right? Okay. So if I wanted to count up all the blocks quickly, I could just do 7 times 6, which is 42. But I don't want both the green and the red. I just want the red. I want half of this. So if I divide this by 2, I get 21. So what's kind of cool is, like, if you had 8 of these, you could do this same kind of scenario. You would take in 8 blocks and then add the 1 block. So you'd have 9 times 8, which is 72. Divided by 2 is 36. So it's kind of cool. You could come up with these sums for bunches of numbers, including up to 100. Okay. Another problem that uses modeling is one that maybe actually has physical models or manipulatives to work with, like this. This is called a domino donut. So pause the video, draw these dominoes here. And what we're going to do is notice that on each side of this domino donut is 11 dots. And I want you to make a domino donut with these 4, but I'd like them to have 12 dots on each side. Okay, so if you need to go back and draw the first one again, pause the video, take a moment, do that. Here we go, though. We're going to attack this. And let me zoom out just a smidge so I can see those dominoes while discussing how I'd approach this. Okay, so first thing I noticed is that the number of dots here are 6 dots total. This has 10, this has 7, and this one has 8. So the one that's different from the others is the odd number, right? The fact that there are 7 dots on one of them, where the other ones have an even number of dots. So I'm actually going to start with that. I'm going to start with the one that's a little bit different and kind of figure out how to best make that one work. So I have 4 dots and 3 dots. Cool. 7 dots total. So I want it to total up to 12. So in order to do that, I need to add 5, and there's only one block that has 5. That's the first one. Sorry, let me zoom out a little bit more again. First one. So I need to go ahead and put that one below. So there's 5 and then 1. Okay. So that has 6. But I technically, in order to add up to 12, I need another 6. And there's the other 2 blocks both have 6. So let me come back to that one in a second. Let me go up to the top instead. So across here, coming back up to this 4, right? I have 4 and I need it to add up to 12. So I need 8 more, which I happen to have a block of 8. Okay. So here, I'm going to go ahead and take my little 8 block. I'm going to lay it down and have 6 and 2. I don't know if this is, by the way, the right order to put it in. I might want to swap it. I might want to do 2 and 6, but here, I'll see in just a second. 6 and 2. Okay, so now that I see that I have, so let's see, there's 12 on this side, 12 on this side. Okay, so in order, with the 2 here, in order to have 12 on this side, I need 10, and I have a block of 10. Cool. So here, if I put the block down, I don't want to put it the way I see it up there. I don't want to do 6 and 4. I actually want to lay the 6 down with the bottom row because this has 6, right? I need that to add up to 12. And I'll put the 4 here. And there we go. So this adds up to 12 on this side, 12 dots here, and same with the bottom. Since I put the 6 down there, there's 12 dots down there as well. Woohoo! We're amazing. Good job. Okay. Let's go ahead and look at the next technique. Let me switch back to black. We are going to, draw a picture. Now I know what you're thinking. Wasn't that what we were doing? Not quite. Technically, before, what we've been doing was just doing models, and it was kind of necessary for us to do some models, like especially in this last one, we had to use a model in order to do that problem because we were given actual geometric figures to work with. The prior problem, I created a way of looking at it with a model. They do kind of overlap a little bit, drawing a picture, creating a model. They do kind of have a little bit of overlap because sometimes the model doesn't have to be a picture. You could technically make a formula, but that's the idea. They're technically distinct in that one might be that you're working with something geometry to begin with. Okay, so for this one, I want to read you the problem, okay? Mr. Jones is throwing a party where he is inviting 22 people. He needs to borrow card tables in order to create one big table for everybody to sit at. Okay, real quick. let me write down some of that information there. So we're having a party with 22 guests. Okay. And we're using card tables. Real quick, just so we know what a card table is. A card table means that it's a square where it's one person sitting on each side, right? Like, so one card table will seat 4 people. Here, I'll use little X's instead of ones. So here's people sitting around the card table. Okay, so we're using card tables. But he wants to borrow as few card tables as he can to form one table. So form one table, one big table. That's a weird looking M. Form one big table. Struggling over my writing here. Writing too fast. One big table with the fewest card tables. All right, that's the idea. Form one big table with the fewest card tables possible. All right. So this actually kind of makes sense to draw a picture for it. And there's a few ways we could do this. So here, let's start with, let's say I have one card table here. I'm going to use X's. I keep switching to ones, but I want to use X's. Okay, so there's 2 people there. And let's say I put another card table right here. So there's 2 people here. And then I'm going to keep adding sets of card tables until I have 22. All right, so let's see. How many am I going to need to add? So if there's already 2 to begin with, I need to add, and there's going to be 2 at the end. Okay, so subtract 4. So 22 minus 4 is 18. So I'm going to need to do this several times, 9 times total. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's it. Okay, so hold on. So 1, 2, 3, 4, 5, 6, 7, 8, 9 across the top. And then 10, 11, 12, 13, and then 9 on the bottom. That'll do it. That'll give us 22. Okay, so how many tables did we use? 18 tables total. That's a lot. And in fact, part of the problem was by stacking them together like that, I lose seats, right? There's a bunch of unused seats by pushing them together. So if I'm smart, it would be probably wise to just line them all up into one long table. Okay. So in this case, here's our first one. And then we have one on each side. And I'll keep that pattern going. So let's see, that's 5, 6, 7. Okay, so here I see I'm going to need 20 on each side. I'm sorry, 10 on each side. So it's 20 total. So 2, 3, 4, 5, 6, 7, 8, 9. Here, I think I didn't need it that long. 10. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on either long side. And then there's the 2 that sit at the head and the foot of the tables. Okay, there we go. That I can achieve with 10 tables. So that would be the best arrangement to use the fewest number of tables possible. And I mean, you could kind of keep drawing pictures until you come up with the arrangement. That's the idea. You kind of draw out until you figure out which one works. There are other scenarios that we could possibly be asked to draw a picture. Let's say in this scenario, 5 people are in a tournament. And they have to play each other exactly once. In a tournament where each person plays everyone exactly once. Okay, so the question is, how many games will be played? All right, so if I'm going to draw a picture for this, and there's a couple ways to visualize this. Let's say we have person 1, 2, 3. Actually, here, let me give them letters for names. Okay, A, B. So A is for Anne, B is for Bob, C is for Chuck, D is for Daryl, and E is for Ellen. All right, there we go. There's our 5 people. Okay, so we're going to pair them all up so that everybody plays everybody exactly once. Okay, so here, A is going to play B, and we'll start with player A. So Anne. Anne's going to play Bob, and then Chuck, and then Daryl, and then Ellen. Cool. And now Anne has played everybody once. Okay, so let's go to Bob. Bob needs to play Chuck and Daryl and Ellen. Oops. Making my circles too small. Okay, and then Chuck needs to play everybody. So let's see. He hasn't played Daryl or Ellen. You kind of hopefully see the pattern going on here. And then lastly, we'll have Daryl and Ellen play each other. And there we go. So this is a total of 4 games, plus 3 games, plus 2 games, plus 1 game. So adding those all together will give me 10 games total. So this visual is just to kind of make it quick to see the pairings. Okay. All right. So those are the first techniques. And then I will go ahead and stop here and give you an opportunity to kind of digest that for the homework. And then I'll give you some more techniques to look at.